For problems 10 through 13, I'm going to rewrite this function, and I want you to recognize if this was a y, where y equals log base 5 of x. This is in logarithmic form. Now we can write this in exponential form by recognizing the base remains the base. We're going to go across the equal sign and raise it to the y value and set it equal to what is directly behind the base, which is x. Now, how are we going to relate that to what we're provided here? So here, this means that we want to plug in 625 for the x value. So 5 raised to what value is equal to 625? Again, here's our x. And so I'm just going to count with 5s here. So we have 5 times 5. 5 to the first is 5. 5 squared is 25. 5 to the third is 125. 5 to the fourth is 625. So the value here for this problem is 4. The output is 4 when x is 625. Let's try the next one. Same concept here. I have 27 raised to what power equals x? And in this case, x is 81. 27 raised to what power is 81? Oh, now this is tricky. Why is it tricky? Because I know 27 to the first is 27. Now 27 squared is going to be far greater than 81. What can I do here? Well, I know that if I take 27 and I raise it to the 1/3 power, that means what times itself? 3 times equals 27. So for those that need a little reminder, 1 times 1 times 1, 27. 2 times 2 times 2 is 8. 3 times 3 is 9. 9 times 3 is 27. So this would equal 3. And I still need to get to 81. So I know that right now if I raise it to the 1/3 power, I'm at 3. Now 3 to what power gives us 81? So 3 to the first is 3, 3 squared is 9, 3 to the third is 27, 3 to the fourth is 81. So I believe that if I raise it to not just to the 1/3, if I raise it to the 4/3, I believe I'm going to get 81, and I can prove that right now using a calculator. Now, we don't want to use a calculator in this portion, knowing that half of our test is non-calculator, but if you watch here, take 27, and I raise it to the 1/4 power, 4/3 power, excuse me, I end up with 81. So the correct answer here for the outcome is 4/3. We can practice more of those in class. It's probably a little confusing for you. It's been several months since we went over exponents. Again, this is going to be 1/2 raised to what power, this is a y, equals the value of x, and x here is going to be 64. So I want to turn 1/2 into 64. Well, one thing I notice is 2's on the bottom. So the first thing I know about this y value is I want it to be negative. Because if y is a negative value, then instead of being 1/2, it's 2/1. Why? Because the negative value says, hey, 1's not happy, it goes to the bottom. And when it's distributed to the 2, 2's not happy, it goes to the top. So now I'm going to ask myself, 2 to what power equals 64? 2 times 2 is 4, 8, 16, 32, 64, 1, 2, 3, 4, 5, 6. Not only is it 6, it's going to be a negative 6. Okay, let's do this one. So we have 4/9 raised to what power equals x? Okay, here. And I want this to equal 8/27. Well, let's see here. How can I turn a 4 into an 8 using an exponent? Well, the first thing I think of is if I take 4 to the 1/2 and I take 9 to the 1/2, that really means like a square root. So I'd have 2 and I'd have 3 at this point. Now, could I raise it to another power to end up with 8? 2 to the 3rd power is 8. 3 to the 3rd power is 27. So I believe that the correct answer here is 3/2, because I'm going to take it to the 1/2 power and then to the 3rd power. So 3/2. Now let's make sure that's right. I can prove to you that's correct by taking 4/9 and I'm going to raise it to the power of 3/2. And let's see if I end up with an answer of 8/27. Okay, well that means nothing to me. I'm going to put it back into the fraction form and you see we get 8/27. If you're somebody who wants to practice more of these, please reach out to me and I can make more problems for you to practice. what do the directions mean here? So we're simply going to find the inverse of this function. Now, as a quick reminder, what does it mean to be an inverse? Let me grab this really quick. Let's go back to very basics. I know I brought some pens in here. Okay, so we have a function here. I'm going to make up a very simple function for us. We have x plus 1, and I'm going to have two circles. Okay. Now, when I plug in, I'm going to choose just random arbitrary numbers. Let's start with the -2. If I plug in -2, -2 plus 1 is -1. What does that mean? It means that 2 maps on to -1. Let's try a -1. -1 plus 1 is 0. What does this mean? It means -1 maps on to 0. Let's do one more. If I plug in 0, 0, oops, sorry here, 0 goes with 1. What does it mean? It means that 0 maps onto 1. All of that is very basic concept. Now, what can we do to create an equation that we can reverse the direction? So I can reverse it and go just backwards here, just backwards, just straight backwards. So now when I plug in -1, I want an answer of -2 as the outcome. If I plug in 0, I want an answer of -1. That's what creates an inverse. How do I find the inverse? First of all, I switch the x and y, so switching the x and y, and then I'm going to isolate the y. So x minus 1 equals y. Now I need to denote it as the inverse. There's my little -1 in the x1 position. Let's see if this works. -1 minus 1 is -2. 0 minus 1 is -1, and 1 minus 1 is 0. It works. So these two are inverses of one another. If a function is 1 to 1, and we reviewed this last week, 1 to 1 means that every x matches onto one unique y. That means there's not going to be another value here. So you can be a function, for an example here, if I go down here and write this. So 3 to 2, 4 to 2, 5 to 2, 6 to 2. This is a function because every x belongs to at most one y. It's a function, but it's not 1 to 1. Because if you do 1 to 1, it means that only one x value matches onto each unique y. And we can see that more than one x. So it's a function. It's just not a specific 1 to 1 function. This would be an example of a 1 to 1. So 3 to 2, we're going to say 4 to 5. And we're going to say 5 to 8 and 6 to 11. Here's an example of a 1 to 1 function because still we have every x that matches onto a unique y. That means no other x is going to map onto 2, 5, 8, or 11. So why does that matter? Because if an equation is not only a function but it's 1 to 1, it means that it does have an inverse. Once again, if a function is 1 to 1, it means it does have an inverse. So keeping all that in mind, how do we find the inverse here? Okay, so to find this inverse, I'm going to go ahead and I'm going to write y equals log base 6 of x. And now our goal here is to switch the x and y, so x equals log base 6 of y. And now how do I isolate the y? Well, I can take this base, and let me switch up the colors so it makes it a little more obvious for us. Whatever this base is, this is now the base, and this is the exponent. Whatever I do to one side, I must also do to the other side. Now on the right-hand side, these are going to simplify to 1. I get to bring down the y. So I have y equals 6 raised to the x, or it could be 6 raised to the x equals y. But I do need to note that this original function said f of x. So this is the inverse. This is the inverse. Now, for all of this to be, all right, I think you guys can see that okay there. So this is the inverse. Let's do the exact same thing here. So this is like a y, so I'm going to switch the x and y, 1.035 raised to the y. Now, how do I solve? The reason we learn about logs is when we have a variable in the exponent position, in order to solve that variable, we use logs. So I'm going to do log base 1.035, log base 1.035. I do it to both sides, and then I drop down what was there. Now, on the right-hand side, log of 1.035 with this number behind is going to simplify to 1, and I have 1 times y, which is y, and log of 1.035 x. This original function was an f of x, so we need to denote it as this specific inverse, log of 1.035 x. Okay, and by the way, they did want us to rewrite it as g, so if you want to put g is equal to this, they're saying define the inverse as g. Now, I personally prefer this because this shows that this is exactly the inverse of this original function. I prefer this, but I suppose for testing purposes, we would say g of x equals 6 to the x, and g of x equals log base 1.035x. Okay, let's do the next one. I'm going to switch this to be x equals 3/4 raised to the y. Again, the only reason we learn about logs is when we're trying to solve for a variable that's in an exponent position. So I'm going to both sides. I want to remove this. So I'm going to do log of 3/4 to the left and log of 3/4 to the right. And I'm going to drop down everything that was there. So behind this is an x, and behind this is going to be 3/4 raised to the y. Okay, these two are going to simplify. They don't just disappear, they simplify into 1. I have 1 times y is y, and log 3/4 of x. Now, I prefer to say this is f of x. We're going to say the inverse of x is log 3/4 your base of x. Remember, whenever you see a natural log, the ln of x, another way to write this is log base e. These are equivalent forms. So the first thing I'm going to do is switch the x and y. X equals log base e of y. Okay, this is similar to this problem. In order to isolate the y, I'm looking at the base, and the base is the number e. It's the number e, Euler's number. So I'm going to take this number e, I'm going to do it on both sides. Now on the right-hand side, these are going to simplify to 1, and then 1 times y is simply y. So I have y equals e raised to the x, and this was f of x, so the inverse of x is e to the x. Over here, I'm going to switch the x and y. So, switch the x and y. This was a y, x equals log. Now we don't see a base. When you don't see a base, it's a common base. So when there's a missing base number, it's really base 10. So I switch the x and y. And now at this point, this is similar to problem 14 and 17. For me to isolate the y, I take whatever that base value is, I'm going to do it to both the left and to the right. So 10 raised to this exponent and 10 raised to the x. These simplify to 1. 1 times y is y, and 10 raised to the x. So the inverse of f is 10 to the x. Before we get started on the next two problems, I want us to look real quickly at these two equations. So we have y equals log base 10 of x, and this is a common log. When you don't see a base, remember it's a base 10. Then I took the inverse of this by switching the x and y and isolating the y, and this was able to get for the inverse. So I graphed them on the exact same Cartesian plane. I also graphed y equals x. So what's really cool here is if we look, there's a couple different things we can see. If we fold it along this green line, we can see that what we see is a graph in the blue and also in the red would align to each other if we folded along the line y equals x. Now, also notice that we can look at the points 0, 1, and if I take these two inputs and outputs and I switch the order, we can see that the input 0 becomes the output for the other function, and the output for the original function becomes the input, and that is the case for all. So if I just choose another random number here, let's choose this one right here. Let's see if we can find 0.3 and 2.0, maybe a little bit harder to see. Oh, here we go. This is a much nicer one. I can get a 0.5 there. There we go, 0.5 and 3.1 about. 0.5 and 3.1, okay. So 0.5 and 3.1, so let's go over to 3.1. 3.1, and there's your 0.5. You can see how the inputs and outputs are just going to switch. So let's come back here, and let's look at what this problem is asking us. State the domain and range, identify the zeros and intercepts, okay, and then determine the asymptotes, identify the end behavior. Okay, gotcha. Let me write this down. So let's get started for this function, just to show you if you somehow don't have a calculator at home with you at the point, we can look what this looks like in Desmos. We have the same basic shape that I've already put onto my paper, which you can see here. But if we go into Desmos, how do we find log? So if you go over to functions and you go all the way down, you're going to find log. Let's see here, did I go past it? Oh, there you go. So this is y equals log base 6 of x. And we can see we get that same basic shape. It goes through 1, 0, okay? Let's come back here. So this is the same basic shape here. This is 1. And so the very first thing we want to do is we want to identify the domain and range. So the domain of function f is going to be all x values such that x is greater than 0. So this is never going to overlap the y-axis, which means that y will never equal 0. Now let's do the range. The range of this function is all real numbers. There's no limit how low it goes, and there's no limit how high it goes. As it moves to the right, it continues to go up. So I've done the domain and range. Let's identify the zeros. So what is the zero of this function? We have an x-intercept at 1, 0, and there is no y-intercept. Why again? Because this function never crosses the y-axis. Let's determine the asymptotes. So we have an asymptote here right along this line that corresponds to the y-axis. So we have a vertical asymptote of x equals 0. That's the equation of the asymptote. Now let's do the end behavior. As the function goes to the far left, what is it approaching? It's approaching negative infinity. And as the function moves to the right, it's oh, you know what here? I think I may have that wrong here. Let's see here. I got to think about this again. All right. So as we're moving to the left, it's increasing as I go to the right, and it's approaching 0 because it's always what is the x value. So I need to go back here. It's approaching 0. As it moves to the left, it's getting closer and closer to an x value of 0. As it moves to the left, it's getting closer and closer to an x value of 0. So it's approaching the vertical asymptote of 0. Now, as it moves to the right, it will continue to go up. All right, let's go on to our next one. Let me see. So I provide you a little picture here. So we can see that our base is 0.5, so it's going to look like this function right here. So if I draw a real quick picture, it's looking something like this. This is still going to be at 1, 0. All right, let's get started here. So the domain of this function is all x values such that x is greater than 0. And the range of this function is going to be, there's no limit how high it goes, and there's no limit how low it goes. So it's going to be all real numbers. Okay, we have an x-intercept of 1, 0, just like the previous one. And again, there is no y-intercept because we have a vertical asymptote at x equals 0. Now, as we go to the far left, again, it's approaching 0. And as I move to the far right, instead of it going up, it's going down. Okay, we're going to apply the rules here. So these rules that I'm talking about right here are going to be helpful for you. If you go back to this first page or see an exponential logarithmic functions, we're going to apply these rules here as they apply to log. It also may help. Let's see if I, oh, here they are. Right here. Properties of logs. That's going to be on your second page. That is going to be helpful as we do this. All right, let's get started with this first one. So how am I going to do this? So it says evaluate the following properties of log functions without using a graphing calculator. Refer to the rules, and that's going to be on the second page here. So for this problem, we're going to do the function, and I'm going to substitute it in for x, e to the 10th. So into this portion, I have the natural log of e to the 10th. I've just simply taken this value and substituted in for x. Now, when you have an exponent, it's going to go in front. So this is going to be equivalent to 10 times the ln of e. Remember, ln, or natural log, is the same as log base e. And these two are going to simplify to 1. Why is that? Because we ask ourselves, e raised to what power equals e? E is a number, so it could be any number. Like, think of this as being 10. 10 raised to what power equals 10? 1. Or 15 raised to what power equals 15. When these values are the same, this is going to simplify to 1. 1 times 10 is simply 10. Let's look at the next one. Okay, f, now I'm going to plug in 64 to the 20th, and that's log base 2 of 64 to the 20th. Now I'm going to rewrite 64 so it looks just like this, where the base is the same as the number behind it. So log base 2, now how can I rewrite 64? 2 times 2 is 4, 8, 16, 32, 64. 1, 2, 3, 4, 5, 6. 2 to the 6th is the same as 64. Again, 2 to the 6th is the same as 64. I'm going to throw this 20 in front, so I have 20 times. Now this simplifies to 1, and now I have 20 times 1 times 6. Well, 20 times 6 times 1 is 120. Let's look at the next one. We have f of 100 over 0.000001. So log, now I don't see a base, remember it's base 10. It's base 10. So I'm going to rewrite this right away as 10 squared. That's the same as 100. And now this is going to be 1, 2, 3, 4, 5, 6. Let's make sure I'm right. 1, 2, 3, 4, 5, 6. 10 to the negative 6. When you have division and you expand it, we're able to do so using subtraction. That goes back to one of the rules you can see on the second page, which is right here. When you have division, it can be expanded. So this is in condensed form. It can be expanded into subtraction. Just like multiplying can be expanded into addition. So I have log base 10 of 10 squared, subtract log base 10 of 10 to the negative 6. So the 2 comes in front, and I have 2 times this quantity, which is 1, because we have the exact same base and the number behind it. The negative 6 comes in front, and again I have log base 10 of 10, which gives you 1. 2 times 1 is 2. Negative 6 times 1 is negative 6. 2 subtracted negative 6 gives you a positive 8. Okay, now here we go. We're going to put this in. Ooh, this is looking kind of confusing. We have f of 8 times 32 equals log base 2 of 8 times 32. Now, just like I said, division, this is in condensed form with subtraction. When we expand it, division turns to subtraction. And when we're multiplying and we expand it, it turns to addition. So I'm going to expand this log base 2 plus log base 2. Now I can rewrite 8 as 2 to the 3rd, and I can rewrite 32 as 2 to the 5th. The 3 comes in front, and I have 3 times log base 2 of 2 is 1, and the 5 comes in front, and log base 2 of 2 is 1, and I have 3 plus 5 is 8. Okay, so let's assume this. If ln of u is equal to ln of 450, then u must equal 450.